All right, so it's the last lecture. So now we're going to switch topics. So far we focused on various fault-tolerant quantum algorithms. And the good things about these algorithms is that we know they will work for sure. So there are rigorous guarantee. And the way it works is that if you use this many gates, then we are guaranteed to get the correct answer if you have a fault-tolerant quantum computer. And we're pretty confident that they will provide speedups, at least asymptotically, and probably also for some practical problems. But these are not going to be implemented anytime soon. At least that's the consensus. So that's the downside. So I'm sure you probably heard that there is a huge amount of recent work on what is known as variational quantum algorithms. So these are quantum algorithms which are heuristic in nature, which means that we don't know if they will actually work in practice. And by work, I mean, we don't know like how well they will be able to approximate ground state wave functions, and we don't know what kind of speedups we're going to get. So that's a big downside compared to these like more traditional approach to developing quantum algorithm. But the upshot is that we can actually implement them now. And the quantum computers that we have are already pretty getting to the point where classical simulation is difficult. So the hope is that maybe there's something that we will like figure out sort of experimentally by trying a bunch of things. And if that works out, that'll be certainly great, but we don't know if that's going to happen. Yeah, so I'm going to tell you about some things that people are focusing on these days, and some like background history, so that maybe if you're interested in this, you can go ahead and look up these papers. And one of the things that people are, that has been very active lately is what is known as QAOA. It's a quantum approximate optimization algorithm developed by Farley, Goldstone, and Gutman in 2014. And the problem is very simple. So you have a classical Hamiltonian. So the C alpha of Z is like an Ising-like Hamiltonian, like depending on the bit string. So think of it like the simplest example is like the 2D Ising model, but then things get more complicated if the interactions are not very magnetic, and also if the interactions are non-local, and if you include like 3-body, 4-body terms. So in that case, this is a, and this, it should be noted that this is a very difficult problem in a sense that we do not anticipate quantum computers to be able to solve the ground state problem of this Hamiltonian in polynomial time. The reason is that, so solving this ground state problem, ground energy problem, is NP hard, meaning that if you can solve such a problem, you can solve any problem in NP. And people do not expect, people expect the problems in NP are hard because many smart people have thought about this and didn't come with a solution. And many smart people have thought about ways to solving NP-hard problems in polynomial time using quantum computer, and none of them could come with a solution. So the current consensus is that you shouldn't really expect to have a general purpose efficient solution for finding the minimum energy of such Hamiltonians. Nevertheless, the hope of the QAOA is that if you consider a specific subset of Hamiltonians, and if you're maybe interested in, let's say, the ground state energy density instead of like the precise ground state energy, then maybe there are some rooms to do better. And the basic idea behind all of this is physics-oriented. It's based on the quantum adiabatic algorithm. And as the name suggests, the quantum adiabatic algorithm is literally applying the adiabatic evolution. So imagine so I already told you this Hamiltonian H, which is a sum of Ising-like terms. And what you do is that you are considering an interpolation between this Hamiltonian, for which we want to know the ground state, and another Hamiltonian, which is just a sum of transverse field terms. Okay, and so as we change S from 0 to 1, we smoothly interpolate between this very simple Hamiltonian for which we know the ground state, which is just tensor part of the plus states, where plus is that. And so if there is a gap along this path, and if you evolve this H slower than the inverse gap along the path, then by the adiabatic theorem, you will arrive at the ground state of this Hamiltonian H at S equals 1. So in that case, you indeed get the right answer. Of course, the key question is, can you actually ensure that the gap is not too small? And it turns out in instances involving NP-hard problems, gap either does close, or even if it doesn't close, the gap goes all the way down to like something that is like exponentially small in the system size. So that's the basic idea of the adiabatic algorithm. And we can consider a trotterized version of this quantum adiabatic algorithm, because at the end of the day, what you're doing is a time-dependent Hamiltonian simulation. So you just apply e to the I, let's see. So you have this time-ordered at the end of the day, you, let's see, actually, there should be another parameter. You're just doing this time-ordered integral, H. Okay, and of course, you can trotterize this, in which case you'll get exponential of the local terms that appear either in H or H prime. And because of our problem definition, all of these terms were local, like it was like a few body operators. So you can certainly apply those gates to approximate the true adiabatic evolution. However, you could maybe hope to do something even less and just hope to get the answer. So imagine you apply this Trotter-Suzuki decomposition of the adiabatic algorithm, but you're not really interested in the actual approximation of this true unitary operator that you actually, you're not interested in approximating this unitary operator per se. You just want to apply some operator which is inspired by this unitary operator, and just hope to show that the answer that you get that way is good enough. And if you do that, the kind of operators, at least when you do Trotter-Suzuki decomposition, the kind of unitary operator that you get is something like this. So you have this interleaved sequence of unitaries generated by H and H prime. And in principle, you should take thetas and phis to be all going to 0 and take n goes to infinity limit. But we just choose a finite n. And instead of choosing these theta ones and phi ones to be very small, you let them be whatever they want to be. And the hope is that you'll be able to choose a good value for these angles, which are in some sense will give you a good enough answer for the ground state energy approximation. So the history behind QAOA is pretty interesting, actually. So let's say the quantum adiabatic algorithm was proposed in early 2000s. And then after 10 years, the similar folks proposed this QAOA. And in the same year, they showed that this QAOA could outperform back in the day the best known classical algorithms for this problem called Max-Lin-2. Okay, so what they did was what was the following. So there's some again, this is some problem for which you want to find the minimum energy, and there is a the dumbest way to do this is to just pick a random bit string and plug that in. And what they could show was a result that is like a slightly better than this random assignment. But this extra increment, the amount by which you are better, was better than the best classical algorithm at the time. And then a bunch of folks, all of these folks are classical computer scientists. So they looked at this paper and realized that, oh, this was very interesting. So they tried to solve this problem using just classical computational methods. And then indeed, they came up with a classical algorithm that beats QAOA. So there was this short fame of QAOA in which it could outperform the classical algorithms, the best classical algorithms at the time. But then this victory was very short-lived. And since then, this doesn't necessarily mean that QAOA is like better or worse than the classical algorithms. It just means that for this particular problem, the best bound that you can guarantee for the QAOA is not as good as the best bound you can guarantee for the classical algorithms. So currently there is still an ongoing debate on whether QAOA can do actually something useful. And in 2019, Hastings provided evidence that there's a version, there's like a classical analog of QAOA, which doesn't use any quantum mechanics, which is likely going to beat QAOA if you have a finite number of rounds. So here we had this number of interleaved sequences of unitaries. And the main point was that if n is a constant that is independent of the system size, then there were some evidences suggesting that this finite depth QAOA is probably not going to beat more sophisticated classical algorithms. Okay. Of course, then one might say that, oh, maybe if we use QAOA using logarithmic depth, so let's say we have n qubits and the depth scales as log n. So again, So if the system size is, let's say, m, if we choose this n to be, let's say, log m, then maybe we'll get an advantage. And maybe that is true. Maybe that is not true. We currently do not know. But that is the current state of affairs for QAOA. But what is still interesting, so we don't know what's going to happen in the future, but what is interesting is that these near-term algorithms, they can be actually implemented in like a fairly large quantum computers. So this is a figure that I stole from a recent Google's experiment. So what they did was that they have their quantum computer consisting of like 50 qubits, and they tried to implement QAOA using 23 qubits. It's still classically simulable, but still pretty interesting and large size, large enough that it takes a bit more work than just a laptop to simulate at a large scale. And as you can see here, so the performance of the QAOA, so P here is the depth. So in 2 slides ago, I showed you these like interleaved sequences of like e to the I theta h0 and e to the I phi h1 prime. So P is the number of such steps. As you can see, as P goes to a larger and larger value, you're supposed to get a better and better result. And indeed, if there's no noise, if you just simulate this thing, this is indeed what you get. But in experiment, as you increase this value of P, you initially get better and better result, but then your result sort of degrades a little bit. And it is very likely that this is because of the effect of noise. So in realistic devices, none of these gates are actually perfect. So every time you apply something, like something wrong will happen with some probability. And so this results like this suggest that unless we make some drastic changes to QAOA, without mitigating the effect of noise, it's unclear if we can get any advantage using QAOA.
So maybe this is a completely silly question, but this this seems like a report of a failure of QAOA at the current experimental setup.
Right. Yeah.
Why is it published?
Well, I don't know. It's a difficult question.
So they did not actually succeed in solving any problem with this approach.
They did not outperform the existing classical computational. They did not outperform the existing classical optimization algorithms.
Okay.
Yeah. Yeah, I don't know. This that's a I can't answer that question.
Yeah.
Anyway, yeah. Okay. So what are the challenges? So, well, what these results? Well, okay. So let's focus on the noiseless case. Clearly, we need to go to larger depths to get a better result. So that's, I guess that was expected. But that's precisely the regime in which we have more noise. And the fact of the matter is the quantum computers in the near term will be noisy. So this is an issue. And if you go to a shorter depths, then you won't be able to beat the classical methods because there are all these like theoretical indications. And also the experiment also shows that they were unable to beat the classical methods. Moreover, I think it's still an interesting problem, but at this point, it is unclear if a speed up is possible, even in principle. So I guess in this case, it's not really the speed up. The question is for a reasonable value of P, the depths of the circuit, can you actually find a better solution in terms of the energy? And maybe that's true, maybe it's not true, but we don't know. That's the bottom line. And lastly, one needs to find a set of good angles. So remember, the QAOA is determined by this unitary sequence of unitary operators. And these angles are, as it stands, they're not like determined a priori. So there are different approaches to do this. If you look at the original paper for QAOA and also its follow-ups, they don't actually propose to variationally minimize the energy by changing thetas. So they actually, for particular problems, find a specific set of angles via analytic derivations, which can guarantee some bound on the energy. So in some cases, you can actually find a precise value of thetas and phis, which will give you the good enough answer. But sometimes it might be actually difficult to do that. So in that case, the variational optimization seems like the most natural thing to do by just doing something like gradient descent. An interesting development lately was due to Brandau et al., in which they showed that theoretically and also numerically show that in some sense, good angles generalize well. So what I mean by that is that imagine you don't know what the optimal angles are, but you just do some simulation using very small, you have some problem family, and you find a good angle for a very small problem. let's say, consisting of 10 qubits. The main point is if you consider extending this family to, let's say, over 100 qubits, the set of angles that you found for 10 qubits is likely to apply very well to these like larger systems as well. So that's kind of interesting because it means that you can do like small scale experiments to predetermine what the good angles are and use those as your like starting point. So these are some interesting ideas, but yeah. We'll see how it goes. Yeah.
So to clarify myself, the previous ideas like the qubitization was basically to try to mimic the unitary evolution on a state. But here in the variational scheme, you're basically trying to minimize the energy.
Right. Yeah.
Okay. Okay.
Yeah.
So the choice of these angles are such that you just get to minimize the energy expectation.
Yeah, that's right. That's right. Yes.
Okay.
Okay, so that is it for QAOA. And I want to now talk about what is known as VQE, which is sort of in a similar spirit with QAOA, depending on how you view QAOA. If you view QAOA as like a fixed angle thing, then they are different. But if you view QAOA as a variational algorithm in which you try to minimize data by some optimization algorithm, then VQE and QAOA are very similar. In fact, if you view the QAOA as that way, you can view QAOA as a subclass of VQE. Okay. So what is a variational quantum eigensolver? The problem that you want to solve is very similar, but in a more, but it's also more general. So you're given a Hamiltonian, but now the Hamiltonian is no longer this classical Hamiltonian. It's some quantum Hamiltonian, like a quantum chemistry Hamiltonian or like a Fermi-Hubbard model or something. And you want to find the ground state energy of the Hamiltonian. And the key idea is to use the variational principle. We all learned what variational principle is. What it says is that if you have a general quantum state, psi, and if you calculate its expectation value, then this is larger or equal to its ground state energy. A slightly more sophisticated version is that for any state rho, its expectation value of the Hamiltonian is larger or equal to its ground state energy. So the whole business here is to find some way to prepare a difficult to prepare the way this works in the VQE business is that you want to use these near-term quantum computers to prepare some quantum state. Okay, we don't know what that quantum state will be precisely, but the fact of the matter is that is some quantum state. So the energy that we're going to get will be variational. Okay, so it'll be some approximation, but obviously, like in any variational methods, there will be some issues, and I'll discuss more about that soon. But I think it's worthwhile to first compare VQE and QPE because they try to achieve something similar, but they do so in a very different way. So VQE is very easy to implement because there are quantum computers these days, and the state that you can prepare in your quantum computer, it can be literally anything. You're still going to get some bound. So if you can do a very crappy job and still do a VQE. In that sense, it's very easy to implement. But here comes a potential issue, two potential issues with VQE. First is that you need to begin with a state that is close to the ground state energy. So for example, if you, let's say your initial state is like a superposition of the ground state. And let's say let's consider a highly excited state. Then clearly the energy of this with respect to the state will be very far from the ground state energy, right? because the energy will be the average of the ground state energy and the energy of this highly excited state. And if the energy difference is very large, then this will just make a big difference. So in that case, obviously, VQE is not going to give you a very good result, because then because the result that you're going to get is just not very close to the ground state. Compare to the case of QPE. So if you apply the same situation to QPE, okay, so I don't need to rewrite this again. So if you apply that thing to QPE, then with probability 1/2, you're gonna prepare state psi 0, and probably 1/2, you're gonna get state psi e. And when you get this state, you will actually measure the true ground state energy. So, and that happens with probability 1/2. So if you just repeat this many times, eventually you're gonna get there. So this is a crucial difference between VQE and QPE. So for QPE, it suffices to have a constant overlap with the ground state. You can even have, let's say, only 1% overlap with the ground state, and you just repeat QPE 100 times, and with high probability, okay, maybe 1,000 times, and with high probability, you'll get, you measure the correct ground state energy at least once. But if you're in VQE, and if you have, let's say 0.1% fidelity with the ground state, then you have no idea what kind of energy that you're going to get. So in order for VQE to work, you need to begin, you need to somehow find a good approximation of the ground state in the beginning. The second difference between VQE and QPE is that in VQE, the scaling error scales like 1/epsilon². And why is that? Well, simply imagine, consider a very simple Hamiltonian, like H equals Z. It's a single qubit Hamiltonian. And okay, so maybe this is not the greatest example, but the point is, when you calculate when you measure the expectation value, you're getting many samples, and individual sample, it'll either say that Z is +1 or -1, and you have to average them. And when you average, the error scales like 1/√n, where n is the number of different experiments that you do, So because of that, to achieve an epsilon error, the number of experiments that you need to repeat is like 1/epsilon². So that's where this 1/epsilon² is coming from. And for QPE, you can do this with order 1/epsilon. So in a regime where the accuracy is important, such as in the quantum chemistry examples, then QPE is more advantageous. And as a matter of fact, people have actually done resource estimates for VQE and QPE for practical quantum chemistry applications. And it is often this factor, the scaling the error, that favors QPE over VQE, even if you have a perfectly prepared ground state wave function. So with those caveats in mind, it is still important to recognize that we can actually do BQE experiments in real life, and that is very interesting, certainly. A notable experiment was done by IBM in 2017 or 16. And this is a typical plot that you are going to see. So you have a device here. So these things are qubits, which are locally interacting with each other. And what you do is that you turn on some, in this particular case, you turn on some very natural Hamiltonian, which is just like there. So it's like a constant on, like a two-body interaction between nearest neighbors. And then you apply some like a local pulses for individual qubits. So you apply some single qubit unitary operations, and you change your angle of theta. So that's like a variational parameter. That's your variational parameter. And what you do is that you you estimate the gradient. So let's say we have angles theta 1 to theta n, then the energy that you're going to measure will be just a function of these things. It'll be a very complicated function, but what you do is that you perturb these angles randomly. And where these delta ones and where these deltas like satisfy certain constraints. And this way you can estimate the gradient in the random direction. And then you do gradient descent. At least that's what these folks first did. So, the energy decreases, then reaches a steady state value. And then what you do is that you compare, well, this is your the thing over here, this is your variational estimation of the energy. And you see that it's not exactly the exact result, but it's somewhat close, okay? So you can get some approximation of the ground state energy.
Question. So how do you calculate the energy for a given set of these theta angles in practice?
Right. So you often have a Hamiltonian, which is a sum of these terms. So you know these alphas beforehand, and once you know that, measuring measuring the energy amounts to measuring this thing, which is so these alpha i's are known coefficients. So all you need to do is to measure these expectation values, and this is very easy because, for instance, if you have a Z tensor product like this, then what you just need to do, let's say on qubit 1, qubit 2, and qubit 3, then you just measure everything in the product basis. And then, well, you get some bit strings like 101 or like 010 or like 000. Well, 101, this will be -1 squared, -1, -1 to 0. So that'll be your like a single shot sample of this operator. So you just average that, and you do that for all the operators. So this can be done in a very straightforward way.
Okay.
Okay. So yeah. And you get results like this. So you can see that, so I already told you that we're assuming that you already know how what the Hamiltonian looks like. And here what's going on is that you change the distance, and that change in the distance will change the Hamiltonian, more precisely the Hamiltonian coefficients. So you do that for each distance, you calculate the variational energy. And at least for these very simple examples, you get something impressive. But mind you that this is just a 2-qubit example. So it's a 4x4 matrix. But you do get something. And the result is consistent with the correct result. It's a simple enough system that we can just solve it exactly. As you go to a larger system size, so here you're using 4 qubits, here you're using 1, 2, 3, 4, 5, 6 qubits. And now you're beginning to see some deviation between the actual experiment and the real result. Okay. And so this is, pictures like this sort of like encapsulate the main challenge of VQE. So we would like to be able to see these two curves like completely overlapping with each other, but there's some discrepancy between the two. And this discrepancy is not a negligible one already at the level of these like small quantum systems. So the goal of all of this in the grand scheme of things is to approximate the ground state energy reliably. And the chemist, they have a very specific criterion. They have this thing called chemical accuracy. And that's basically 1.6 milli-Hartree. I forgot what Hartree is in joule, but the important thing is the unit here is in Hartree. So what you aim for is typically the deviation of the correct energy from your the deviation of your result from the correct energy to be less than the chemical accuracy. And you can see that this discrepancy, I don't know the exact number, but it certainly exceeds the chemical accuracy because let's see, this is like 0.1. So, and what you need is like roughly 16% of that. And I don't think I think this guy is comparable to that. So I don't think this has achieved the chemical accuracy. So just like in QAOA, somehow maintaining ensuring the chemical accuracy using these noisy devices is a very challenging problem. But whatever the case may be, these quantum computers are getting better. So maybe in the future, maybe they'll be able to do something useful. We'll have to see. But in order for that to work, there are some things that needs to be done. And there are all sorts of things, but I would say the two of the most important things are first the ansatz that you are using, and the other is how to actually find the lowest energy state within this ansatz. So I'm going to tell you a little bit about that, about the current challenges. So ansatz, as I said, the whole premise of the BQE is that the quantum computers can prepare some quantum state. So really anything is possible here. But obviously we know from our experience in all sorts of variation methods, usually there are like a better ansatz. Usually you have a system that you have in mind, and usually there's an ansatz that works well for those systems. So in principle, you could consider a completely general unitary operator applied to the quantum, to the initial, let's say, product state. And that will be good at approximating any quantum wave function, but it will have some limitations that I will tell you later. And there are these like different methods called like UCC or the Hamiltonian variation method or tensor network, which all are good in their own respective regime. To be more precise, the general unitary, if you can actually do that, then it'll be good for anything. The downside is that if you have a n-qubit system, and if you want to synthesize an arbitrary unitary, then this will generally take a time exponential in the number of qubits. So that doesn't seem like a great idea, even if you have a fault-tolerant quantum computer, because then to solve this difficult problem, you're using exponentially many quantum resources, and that just doesn't seem like a great thing to do. And these other methods, such as like unitary coupled cluster, these are ansatz, which was developed by the quantum chemistry community back in the days, I think in the certainly before 2000s, and they have been resurrected in light of this development in quantum computing. And there are these Hamiltonian variation methods, which is in the spirit of this QAOA. So in the QAOA, we had this like two Hamiltonians, H0 and H1, which we could smoothly interpolate between the two. And we considered like a trotterized version of the adiabatic evolution. So we had like I to the e to the I theta H0, e to the I phi 1 H1, e to the I theta 2 H0, e to the I phi 2 H1, And the Hamiltonian variation method is precisely of this form, where Yeah, H0 and H1 are both structured in such a way that breaking this down into local gates is very easy. And it's plausible to think that the states that are adiabatically connected to another state, if you begin with some fixed states, phi, for those states, it's reasonable to believe that the Hamiltonian variation method will work. And there are things like tensor network models, such as tensor network methods, which are likely to apply very well for locally interacting many-body systems, possibly with a gap or something. But there are still significant amount of challenges. So we can use all these different onsets, but there's a general set of, let's say, like a no-go. I think of them as like a no-go theorem, which tells us not to go in that direction. And one of them is the barren plateau. So what this says is the following. So for concreteness, suppose, so these details don't matter too much, but for concreteness, let's say I want to study a locally interacting quantum spin system in 1D. And what I do is that I'm gonna use an onset that looks like this. So these are like 2 qubit gates. And I just repeat this pattern. Okay, I'm not gonna, yeah, let me just draw the legs here. So you apply these gates and you just repeat this pattern, let's say D times, okay? And obviously, as you increase D, you'll be able to probe more and more quantum states. So the natural instinct would be that you just increase D to oblivion. Like let's say you have 0 error, then the instinct would be to just like make D as big as possible, like 100 or 1,000 or something. But it turns out then there's an issue. The issue is that, let's say this D is very large. So what you're going to do is that, let's see, so this is time. So you begin with some simple product state, let's say 0 state, and then you apply this complicated quantum circuit, and then you measure some local expectation value, which is like the term in the Hamiltonian. For concreteness, let's say I measure the sigma z operator on this site. And then what you would probably want to do is that each of these gates will be accompanied with some angles. So what you would do is that you would calculate the gradient of this thing with respect to these angles. The main point is that as D gets larger and larger, the typical magnitude, at least for typical circuits, this thing decays exponentially with depths. So while it is true that you can probe a larger set of quantum states by increasing the depths, you shouldn't do this so blindly. To the extent that you just start with a ridiculously large depths and try to do gradient descent, because in that case, the gradient will be like 0 almost everywhere. So you won't know which direction to go to minimize the energy. You're just gonna be in this like a large, like a very flat land, and you'll just like roam mindlessly. So this is one issue that you should be mindful of when you're using variational quantum eigensolver.
But this is obviously the same problem that arises in the deep learning architecture.
So I don't know much about deep learning. So
yeah, mathematically, this is, I mean, you get this exponentially small gradient because you basically have to apply the chain rule. Yeah. And
I see.
yeah. So, I mean, it looks to me that mathematical problems are really the same, and there are ways to sort of get around this barren plateau issues in the deep learning. That's why deep learning is so popular. So
Mhm.
maybe you can somehow import some of these techniques.
That would be interesting. Yes, that would be
Yeah.
very nice.
Okay.
Okay. And there's this issue of optimization algorithms, right? Because um, even if it is, well, generally speaking, the energy landscape with respect to these angles will not be a nice like a convex landscape. And in practice, indeed, like people have actually done the experiments, and you can do it on yourself. And often it is very rare that you get like a very nice like a convex landscape. So because of that, like a strict, let's see, a very naive version of the gradient descent does not always work. Obviously, this depends on which onset you use, but if it's like deterministic, if there's no like stochasticity, then you're gonna get stuck. Um, so we need to understand how to avoid them. So this is another issue with these VQE type of algorithms. And the crucial, in my opinion, one of the most crucial issues in the near term is error. Uh, so let's say we somehow avoided all these problems like the barren plateau and all that. Let's say we have already found the optimal angles, and all we need to do is to just run this quantum circuit and measure the energy, and we'll get a good energy compared to any of the best known, any of the existing classical computation methods. Even then, there is an issue because obviously, if you have a larger and larger quantum circuit, the larger the quantum circuit is, the more noise you will accumulate. And let's see. So unfortunately, so there are some techniques which were developed, and the idea is very simple in general and useful. And the idea is somewhat paradoxically, you basically increase the error and extrapolate. So it's kind of counterintuitive because you would think that to reduce the effective noise, you would just try to work really hard to like minimize the error as much as possible. But here the trick is the following. So imagine you have this theta 1 and theta n, this energy which depends on a bunch of these angles, but also on the error epsilon. So what you do is that you increase epsilon and you measure, so you fix the angles to be the same. So theta 1 to theta n, they're just a fixed thing. And you're just increasing the error somehow. And I'll tell you how you do that. But then what you do is that you see some trend. So you get some data point, let's say here, here, here. And then what you do is that you do the simplest version of these methods. What you do is that you do like linear fit in terms of epsilon. Of course, you could go to like quadratic and like cubic fit, etc. But you do that, and then you take epsilon goes to 0 limit. So that'll be B. So it might seem like a kind of a dark art, and to some extent it is. In particular, it's unclear if you're actually respecting the variational principle. That's a big issue. But at the very least, it was proven by these folks that if the depth of the quantum circuit that you're applying is bounded, and if you make some assumptions about the error model, then this actually, the error is not uncontrolled. So you can prove that in that case, after you do this, the B obtained from experiment minus E, let's say the true ground state energy. This is really bounded by order epsilon square instead of like order epsilon. Okay, so since these kinds of work appeared, there have been like all sorts of variants which try to generalize and extend these methods to other settings. And it'll be interesting to see if these methods become good enough to actually lead to a quantum speedup, some quantum advantage in simulating some quantum many-body problems. Yeah, so as you can see in BQE, there are lots of things to be done. It depends on how you view it. So nobody knows if this will actually become useful or not. But if you believe in it, then there are lots of things to be done. So more error mitigation techniques and will be certainly desirable, and rigorous analysis on the approximation error. So what kind of ansatz would be better? And what kind of circuit depths do we need to actually approximate the ground state wave function reliably, let's say up to some area epsilon? And in terms of the geometry of the quantum circuit and the gates, how would the actually error scale? And how does the energy landscape look like depending on the different onsets? None of these questions are very, very well understood. So if you are excited about this opportunity, then there are all these interesting but challenging problems that needs to be resolved. So my point of view is that, okay, so certainly a great attention has been given to these algorithms. And I think it is still important to consider algorithms that would like provable guarantee, because well, it's important to know when things work or when they don't. But perhaps there's an opportunity here in that there's a new field emerging, and maybe these open questions that I mentioned in the previous slide, they might actually lead to something. So I guess we'll see how that goes. So with that, yeah, I'm done with the lectures, and thanks for sticking with me all the way to the last lecture. Thank you.
Well, thank you so much. Thank you. This has really been a special opportunity for all of us. So I think maybe I missed the part where you actually go into the details or the theory of the VQE.
Yeah, I guess there isn't much of a theory. I mean, it's really just well, I think it's just this, literally. Then you can ask, well, I guess the only thing is this rho. This is a state of a quantum computer. That's, I guess, I think this is pretty uncontroversial. Yeah, I think this is basically what VQE is about. But there are lots of other related questions, like how do you actually prepare good states for given for a Hamiltonian? I mean, by good, I mean Lorentz states.
Yeah, I guess what I'm confused about is what's the difference then between QAOA and VQE?
Good. So it depends on how you view QAOA, because QAOA, these angles, where were these? So where was it? Yeah, so these angles, in some versions of QAOA, you just choose them and you just never optimize. And you either do that analytically or just have a predetermined set of angles. In that case, it's hard to say I mean, the energy that you're going to get is certainly variational, but it's not like you're changing something. Oh. So in that version, it's hard to call it as variational. But if you are actually changing the angles, yeah, then that yes, that is a subset of BQE.
Okay.
Any other questions?
Yeah. Okay, if there are no last minute questions, yeah, I kind of feel sorry that we have to stop, but hopefully there will be other opportunities to invite you back as a speaker or lecturer, and
Oh yeah, sure. Yeah,
to
I'll be
continue to
happy
share
to.
your knowledge and experience with us. So yeah, thank you very much.
Okay, thank you.
Yeah, I really
Thanks,
appreciate it.
everyone.